Hello, my name is Dennis Newton at Fowler High Precision. Today we're looking at the Trimos Mestra Touch height gauge, one of the most accurate height gauges in the world. The accuracy on this gauge is 20 millionths repeatability, and the total linear accuracy on this gauge also is 1.5 microns or 60 millionths of an inch. So let's start by switching on the gauge. As the gauge boots up, this is basically a computer with a touchscreen control. And as it goes through the boot up procedure, it will ask us for a referencing. Basically, this point here is the reference point on the column of the gauge. So we move our probe through that reference point here. And once it captures that reference point, it sets up the point-to-point correction on the scale. Then it asks for the probe qualification. This 1-inch setting mask that comes with the gauge. And all I have to do is to qualify the probe is to follow the on-screen instructions here and touch first down and then up, and then repeat the exercise. You'll notice that the gauge takes the hit itself. I have no control over the gauging force. So once that probe constant has been established, it puts that into the buffer. The buffer is 999 data records long, so basically it will compile your report as you measure your part. So now we can move on to measuring some basic dimensions. So I'm going to set 0 off my surface plate. You'll notice that you do get this symbol on the side turning to green. That means it's in the pressure zone that the gauge should have as it's touching the surface, and then it's taking the data. I push the zeroing button. This is a very simplistic key here, very simple to use. There are very few icons on there, but this is the zeroing key right here, as the icon suggests. As I move my gauge up, I can move the gauge with the air bearing that's built in. It's a built-in compressor, and place my probe on the surface, and the dimension goes into the buffer. You can see it displayed in the large display here. Then I can move to a different parameter. This is a different height. As I take that dimension, it's recorded also in the buffer. Now if I wanted to know the differential between the last two measurements, I can simply hit this number 3 key here, and it's a calculated dimension that goes into the buffer. So I don't have to lose my 0 point off the surface plate. And if I want to measure something other than a surface, I can take my starlight and select the diameter mode. The icon here changes to the diameter symbol, and now I can come in and take a measurement. For example, the ID of this particular feature, all I do is place my probe on the surface here, and I can move the gauge or the part. So as I move the gauge through the reversal point, it captures that bottom dead center. You can see here the arrow moving as I move through the reversal point. The green point here is the reversal point itself that it captured. Then I go to the top of the feature and move it through the top reversal point. There it is, it's already captured that value. So what we have here is my centerline position and my diameter of the hole displayed simultaneously on this display. The diameter and centerline are then recorded into the buffer, and one of the things I can do is actually make my centerline my new datum if I wish. I'm in reference 1 at the moment. I'm going to reference 2 and set 0 in my reference 2. So the centerline now is referenced in 0 in the reference 2 mode. Then I come up on my OD, and here I'm checking the concentricity between the bore and the OD. So you can see here that we had a diameter of 0.98429, and the differential between the center lines is, in this case, it's 3/10 40 millionths, and it's a plus, so it's the OD is above the center line of the ID. If you prefer not to use the graphic showing the reversal point being captured, we can switch that feature off. In this case, I can go back into my feature, for example, here, and when I place my probe on the surface here, it doesn't switch to the graphic. It just simply shows you the counting, and as I go through the reversal point, it stops counting, so you know the reversal point has been captured, and you can simply go to the top and again sweep through the top dead center, and as we go through that top dead center, you will see that now is locked, and that establishes the reversal point. So that is one option that you can use. Now we're going to check a few slot widths on this component. I've rotated the component to enable me to measure these slot widths, and I'm still going to be using diameter mode here, even though it's not a circular feature. So as I come in, I'm still zero off my surface plate in reference 1. I can touch up and down, and it shows both the diameter and the center line of the feature. If I want to compare the center line of that slot to this inner slot here, it gives me the center line and the width. It's listed as a diameter, but I can use my calculation key to show that we only have 40 millionths difference between the center line of the two slots. Then I can move up again to my slot here, touch up and down. It gives me both my slot width and my center line, and the center line of course is from the surface plate. I can use my calculation key and it will list the calculated dimension between the last slot as 1.47660. Now I can come up to this slot, and again I'm still reading off the surface plate, so now it's giving me my slot width and my center line, and then calculated difference is 1.06308. So you can continue with measuring slot widths if you have a series of them without having to reset zero every time. Another thing that this gauge does very easily is to measure angles. What I've done here is selected a 2-inch gauge block, and I'm going to use that in conjunction with this parallel bar that will sit between the two bearing points on the face of the gauge here. So I simply position my gauge with my parallel bar and select the position so it will allow me to put the probe against the angle here. And the icon that's shown on here is already the angular measurement feature, so this number 2 key allows me to go into the angle measurement. I've already told the gauge in the programming, function programming, that I'm using a 2-inch gauge block. So basically you just take your first hit at the bottom of the slope, remove your 2-inch gauge block, move the part up to the parallel bar. So my second gauging point is exactly 2 inches from the first, and then it calculates the angle from the 2 hits. It just triggers it out. Now we're going to switch to checking perpendicularity with this gauge. What you'll see here is I've mounted a special probe that's an accessory. It's not included in the price of the gauge. This is for checking perpendicularity, and it's connected to the back of the display here, and it allows you to see both the change in deviation from vertical as well as the height. So we go into our perpendicularity mode. This number 1 key has an icon here to suggest that that's the right one, and you'll see here as I move the probe, the large display changes. So what I'm going to do is engage my probe onto the part, get in the working range here, and then I'm going to set 0 on both scales. So we're starting from a 0 point. As I move the probe up the vertical surface, you see the deviation taking place here as the height changes. As I scan in this vertical surface here to the end of the assessment length, I can stop there and I hit enter to tell the gauge I've finished. Then it starts computing the correlation between the vertical and the deviation from vertical and the height. So this presents then a graphical representation of that surface that's self-scaling. If I check here, it actually does a best fit line between these points, and the green line is the angle, is what's the median values, It's a best fit line through the median values here. And the width of the blue line is the rectangularity, or TIR if you wish. The actual numeric data here of the values measured, this is the distance traveled, just over 6.4 inches. Perpendicularity is 1,008 tenths 50 millionths. The angle is 89.98476, and the rectangularity, or the width of this box, which is kind of a reliability figure, is 3 tenths 40 millionths. And you can actually print that out as a report. That makes it a very nice report. As I come out of this mode, by hitting enter, all that data is transposed into the buffer. That becomes part of the report. Now we're going to switch to 2D measurement. And for quickness, I'm going to check this patch of 5 holes here. Obviously, these outer hole ring of holes are a bowl hole circle, or PCD. And I'm going to compare the XY coordinates of that and compare it to the center hole here. So to start 2D, all I do is open up this submenu at the bottom here and check on 2D and confirm, and we just start measuring the part. Now, if you had a lot of features on the part you hadn't measured before, you may want to number them with a pencil or something like that to record which sequence you measured the holes in, because you do have to replicate that when you do the rotation. So we basically come into the first feature. I'll call this my feature number 1, and what we can do here is touch down on the feature, sweep through the reversal point and go to the top, and then move on to our next feature, number 2. Here it actually tells you that you're in the y-axis, and with the second feature, and we've got to check on the bottom of the hole, keeps track of where you are. Go down to the third feature. Just make sure you go to the reversal point. You can use the graphic, but I prefer to use it without. And finally, the center hole here. At that point, we are finished our 5 holes, so I need to do the rotation to get my XY coordinates. So I hit the angle key here, and here's the gauge differs from all our competitors, and you can select your angle of rotation. It does not have to be 90 degrees. It's by 90 degrees by default, and this part does have a nice 90-degree angle, so I'm going to utilize that. You can actually rotate anything between 45 and 135 degrees. So here we're going to rotate in a counterclockwise direction and confirm that we've done the rotation. So now we measure the same holes in the same order that we did before. This is in my axes now. It's in the x-axis. So that's hole number 1. Notice as I'm moving the part, I can move the part or the gauge, whichever is more convenient. It knows exactly where you are. Here it's telling me on my 4th hole, and I've got to measure the bottom of the feature. And then finally the number 5 hole. So it knows I've finished. It goes to the reports page. I'm going to show you that in a little bit more detail here. So this screen, as we see here, presents the results of our 2D measurement. Basically, we have different boxes here. The yellow box at the top is where you want to manipulate the data to present it the way you want to see it. Here we're taking direct measurements in this blue box. And then down on the bottom here, we've got our tabulated results, holes 1 through 5. The X and Y coordinates are listed down here, and all the diameters are listed down here, as you can see. And the origin is something that I can change. The XY coordinates there are listed, but from who knows where. So when I hit enter here, we can go back to our results page, and this is where I can start presenting the data the way I want to see it. So here I can set a new origin. My origin can be a feature number or a XY coordinate. So I'm going to call the center hole number 5 my origin. So I'll just type in number 5 here and hit enter. When I go back to my tabulated results in here, you'll see that 5 is 0, 0, and all the other coordinates have been shifted accordingly. The diameter is still listed down here. Now I'm going to do an alignment. This part may have been sitting on an angle plate at some kind of irregular angle. So I can make an alignment between features. And this column here is where I'm aligning between features in the horizontal plane, and similarly lining between features on the vertical plane. So we can select this one, for example, where I'm selecting 2 features to align between, or I could select here between my origin and a feature, or my origin and an angle. But here I'm going to select 2 features in the horizontal plane. And I simply type in this case I'm going to align between feature 1 and 2. Select the box down here, and now you'll see in this table we have number 2 and number 1 aligned exactly in the Y axis. So they are both 0.83603. Hit enter to come out of that. So we've done an origin, we've done an alignment. Now I'm going to do a bolt hole circle. This icon here allows me to do a bolt hole circle. When I select that particular icon, all I have to do is tell it which features I want to consider as a bolt hole circle. In this case it's holes 1 through 4. Obviously 5 was not part of the bolt hole circle, so I just hit 1, enter, 2, enter, 3, enter, and then 4, enter. When I've finished inputting the holes I want to consider, hit enter once more, and then it gives me the opportunity to make a feature number for the center point of the array. So here I'm going to select 6 because we already have 5. So my table now has a 6th feature, which is the bolt hole circle, and also it shows you the actual diameter of the bolt hole circle. You can see the bolt hole circle is pretty close to our origin, which is number 5, but it's not a perfect part, which is expected. So you will see in the table here also it gives you your PCD, or pitch circle diameter, or the European terminology for a bolt hole circle. It gives both the diameter and the min and the max diameter. You see it's not a perfect fit, and the XY coordinates of that. So once we've got all that raw data in the table here, we can play around with it even more. So at the moment it's in Cartesian, but I can select polar. So if I select this icon here and switch back to my table, the table now is showing the polar coordinates. So it's the radius for my origin, the angle, and the diameters again listed down here. So you can select either polar or Cartesian coordinates. If you want to get direct measurements between features, this is a point-to-point measurement here. So I can select features, say, between 1 and 3, for example. I can type in 1 and 3 and hit enter, and then in the table here shows me my distance between holes 1 and 3, the center lines, and it gives you both the straight line distance and the XY coordinate distance as well. If I want to measure an angle like this, for example, I can check here, and so if I want to do the angle between 1, 2, and 4, it should be 45 degrees. So let's have a look. 1, 2, and 4. Hit enter. And then in the table, it's 45.01732. So you can do a lot of measurements and play around with the data without losing your original data. Anytime you want to recall the original data, this icon here is selected. So measuring in 2D is very simple. Once you've finished all your measurements and you've got all the data in your buffer, you can select either to store the buffer or to print it out, or both, of course. So it does have a USB stick at the back, memory stick support, so you can dump the data to that or store it on the hard drive of the computer itself. So that is the Trimos Mestra Touch High Gauge. Thank you very much.